kids, this is your ma'am Akshata and I would like to welcome you all to PW Gulf. In our session today, we shall be summarizing none other than the chapter Atoms and Molecules. We have previously learnt about matter, alright, and we also understood whether matter around us is really pure or not. But there was this one statement that we came across, which was that matter is made up of tiny entities, tiny particles. What are these particles about? That we shall be learning in our session today. But before we dive into our session, let's first try to answer the question, can we divide matter? Now that is a question which not just you and I have right now. You will not believe this, but ages back, years and years back, there were a lot of people who were wondering about this question. In fact, Maharishi Kannad said that, you know what, matter, he called matter as padarth. And he said that this padarth or matter can be divided until it cannot be divided anymore. And the particle which we arrive at after it cannot be divided anymore, he called it Parmanu. Similarly, the Greek philosophers, Democritus, he said the same thing. Even he believed in the same thing, that you know what, that matter can indeed be divided into smaller particles. But these contexts that they had, it did not really have a strong experimental support. They were not able to explain it scientifically. It was merely based on philosophies. And then came Lavoisier, who said that there is a law, there are laws of chemical combination which had law of conservation of mass and law of constant proportion. Before we dive into law of constant proportion, I want you to understand law of conservation of mass. Now, what is conservation? Conservation is to save, right? Conserve is to save. Now, law of conservation of mass states that matter can neither be created nor destroyed. In simpler terms, if I have to say that if X grams of reactants are reacting, then we will get X grams of products. That is, mass cannot be created nor destroyed during a chemical reaction. Alright. Then what is law of constant proportion? So talking about law of constant proportion. So Lavoisier, he said that, along with other scientists, he noted that many compounds were composed of two or more elements and each compound had the same elements in the same proportions. I decoded for you. Let's talk about water. Alright, whether you get this water from the river, from the ocean, from the tap, no matter where you get water from, water has two elements, that is hydrogen and oxygen. And this hydrogen and oxygen combine in a definite ratio, of their mass. That is why it is known as law of constant proportions. It is also known as law of definite proportions. Let's say that there is hydrogen and oxygen which makes up water. Alright, they always combine in the ratio 1:8. Why is it so? Why is it so? Now there is hydrogen. Okay, hydrogen and oxygen. We know two atoms of hydrogen combine. The mass of one atom is 1 into 2. So here it is 2 is 2. Oxygen 16. In the simplest ratio, it is 1:8. 1:8. That is, if 9 grams of water is decomposed, you will definitely get 1 gram of hydrogen and 8 grams of oxygen. Alright. So it was Proust. Please notice the scientist, it was Proust who stated that in a chemical substance, the elements are always present in definite proportions by their mass. You have to ensure that you say the term mass. By their what? Definite proportion of what? Definite proportion by their mass. Alright. So other elements like, other compounds, I would rather say, like ammonia. Ammonia, nitrogen and hydrogen are always present in 14:3 ratio, no matter where you obtain this ammonia from. I hope with this, law of constant proportions is clear to you. Now moving on to a diagram to understand this. So for understanding law of conservation of mass, you can see that here methane is interacting with oxygen to get carbon dioxide and what? Water. And look at this. 16 grams of methane is combining with 2 into 32 grams of oxygen to give rise to 44 grams of carbon dioxide and 2 into 18, that is nothing but 36 grams of water. So when you take the sum total of the reactants and the products, you will see that 80 grams of reactants combined to give rise to 80 grams of the product. Alright. So here is an example of law of conservation of mass. Okay, before you think about what a reactant is, so substances which combine are known as reactants. Okay. Now these reactants, they combine, they react and they give rise to products. I hope it is clear, kids. Alright. Now moving on to law of definite proportion. Now here we have a set of examples, right? 2 atoms of hydrogen, 1 atom of oxygen, 1 unit of water. Alright. 4 atoms of hydrogen, 4 atoms of oxygen, 2 units of water. Alright. But the ratio is going to be same. 1:8. The ratio is going to be same. Alright. Now, when all of this was happening, right, this law of chemical combination was given, everything was given, there was no scientific basis. So Dalton proposed Dalton's atomic theory. But before we think about what exactly is Dalton's atomic theory and all of that, let's first understand who Dalton is. So Dalton was a poor weaver's family, born in a poor weaver's family in England. That is not what is important. He spent most of his life teaching and researching. And he was a polymath. Mathematics, physics, chemistry. He had knowledge of a lot of subjects, right? He was a polymath, all right? And in 1808, he presented his atomic theory, which was a turning point in the study of matter, which indeed was the turning point in the study of matter, because it gave a lot of clarity to us chemists as to how these atoms exist, how do they interact, and his theory was based on law of conservation of mass and law of definite or constant proportions. Let's see what his theory stated. Alright, so according to Dalton's atomic theory, all the matter, alright, focus, all the matter, whether an element, a compound, a mixture, whatever you call it, is composed of small particles called atoms. Alright, they are composed of small particles called atoms. No matter what matter you're talking about, be it an element, compound, mixture, they are all composed of or made up of atoms. Alright, the postulates of this theory were stated as follows. Now, these were postulates. Postulates are more or less like facts. It is given and one has to accept it. Alright, so all matter is made up of very tiny particles called atoms, which participate in chemical reactions. This is what he said. Then, atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Now, focus on this statement. Atoms cannot be created nor destroyed in a chemical reaction. Alright. Then he said atoms of a given element are identical in mass and chemical properties. They are identical in mass and chemical properties. Atoms of different elements obviously will have different masses and different chemical properties because they belong to different chemicals. Simple. Then, atoms combine in the ratio of small whole numbers to form compounds. Alright. Now, this atoms combine in the ratio of small whole numbers to form compounds is based upon law of definite or constant proportions. Okay. Now, here he is saying that these atoms participate in a reaction, and then he is also saying that it cannot be created nor destroyed. Now, please, going back to what we learned in law of conservation of mass, that is, mass can neither be created nor destroyed. These atoms make up the compounds or elements that are interacting. Agreed? That is what is being said over here. And he's also saying that, they participate. So it is the atom which is participating in a chemical reaction. And atom cannot be created nor destroyed. So is it not based on law of conservation of mass? It is. All right. Then the relative number and kinds of atoms are constant in a given compound, obviously. Right? So this is about Dalton's atomic theory. Now moving on to what exactly is this matter really made up of? All right, we're talking about matter, Dalton's atomic theory. But what is this matter really made up of? Ta-da! Atoms! Atoms are the building blocks of matter. Now look at this kid over here, this stick figure over here. What is he trying to do? He's trying to build a wall, right? That is what we're able to understand, that he's trying to build a wall, right? And how is he doing that? By adding brick by brick to the wall. Now this brick that he's adding to the wall here is similar to the atom that I'm talking about. The wall here is similar to the matter, the bulk of the matter, and the brick here is similar to the atom. When you put these bricks together, what you get is a wall. When you put atoms together, what you get is matter, right? Then how big is an atom really? Now you can see over here, there is an apple, there is a cherry. Like, how big really is an atom? Is it as big as an apple? Is it as big as a cherry? Is it smaller than a cherry? Or, is there a comparison? What exactly? Like, how big is it really? So atoms are very small, so small that we can imagine or compare it with. They are the smaller things that we can imagine or compare anything with, all right? And more than millions of atoms, when stacked together, would make a layer barely as thick as this sheet of paper. The sheet of paper that you're holding. When millions of atoms are stacked together, what you're able to hold is a thin sheet of paper on which you're taking down the notes, right? So these atoms are really tiny. They are minuscule. And here is how minuscule it is. Here is how minuscule it is. All right, how minuscule it is. So you can see the size of an apple, 10 to the power minus 1 in meters. And look at the size of atom of hydrogen. Molecule of water. See, you have to understand, atoms make molecules. Molecules in turn make up compounds. All right. So you can see the comparison yourself. You can see the comparison yourself that here the size is varying. The size is varying. All right. Moving on. Now, if atoms are so small, you must be wondering, ma'am, atoms are so small. Why do we have to learn about it? How is it like of any consequence or, relevance to us? Well, it is. It is. Now, you must notice the bricks that make up the wall. They'll determine how strong the wall is. If the bricks are not attached properly, if you use a different, kind of brick, instead of using the good quality of brick, you will notice that the bricks in turn, decide the property of the wall, whether how, big it's going to be, how durable it is going to be. Similarly, these atoms which make up the bulk of matter, they decide the chemical properties, the physical properties of matter. All right. So, this is because, the answer to that question is over here. This is because our entire world is made up of atoms. We may not be able to see them, but they are there and they are constantly affecting what we do. Through modern techniques, we can now produce magnified images of surfaces of elements, surfaces of elements, all right, showcasing the atoms. But the thing is, you have to understand that it is the atoms, all right, it is the atoms that are participating in the chemical reactions. We better know about them, because how will we know what kind of a reaction is taking place if we do not know about this, right? And then other than that, it is these atoms that make up the property, the chemical property, the physical property of the bulk of matter. Thereby, very important. All right. Moving on. Now, how do we depict an atom? Yes, ma'am, we have learnt about atom. All right, ma'am, they're important to us. All right, ma'am, that they are small. They are very small that we cannot see them. All of that is clear, ma'am. But how do we depict them? So here is the answer. Dalton was the first scientist who was like, you know what? Let's use symbols of elements and every very specific sense. And he came up with these symbols. All right, this hydrogen, carbon, he came up with these symbols. But if you'll notice clearly, aren't these symbols confusing? Aren't these symbols confusing? Right? The copper and the gold, are they not confusing? They are, right? Carbon and oxygen, are they not confusing? They are, right? So, what happened was Berzelius suggested symbols of elements, okay, be made from one or two letters of the name of the element. All right. And one more nice thing about Dalton was that these symbol, okay, also told the quantity of that element. That is, one atom of that element was depicted by one symbol. All right, but again, this was very confusing. So Berzelius was like, you know what? Let's take first two letters. All right, the first letter of the first two letters. And how did he do that? Here. So in the beginning, the names of the elements were derived from the place where they were found the first time. Example, the term copper came from Cyprus. All right, copper came from Cyprus because it was first found at Cyprus. All right, and then other than that, also from specific colors, like when you talk about gold came from the English word meaning yellow. All right, but nowadays IUPAC, International Union of Pure and Applied Chemistry, it is basically an organization. And it is a international scientific organization which approves names of elements, symbols and units. Ma'am, why do it has to approve, ma'am? Like, what is the sense of that, ma'am? You must be wondering about that. Now listen, Kate, it is very, very important that you think of it this way. Today, what we are learning is at a very, minute and minuscule level. However, a lot of research goes on. A lot of, compounds are reacting. The scientists are working on a regular basis. And they are coming up with, products. They're coming up with products. Now, the thing is, if at one place, if elements start having localized names, what will happen is there will not be any uniformity in the field of research. All right. Other than that, I might call it X. Somebody else might call it Y. We might be discussing the same thing, but we probably are naming it differently. All right. So in order to maintain uniformity, organizations like these, they give scientific names. All right. And it is a very scientifically, oriented and scientifically organized methodology. All right. And one second, my pen fell down. All right. So many of the symbols are the first one or the two letters of the element's name. In English, the first letter of the symbol is always written as a capital letter, that is in uppercase, and the second letter is always written in lowercase. All right. Let's look at the examples. Now, when you look at hydrogen, H, hydrogen. Helium. Now there is ambiguity between H and H. So we take the second term, the second letter E, and we write it in lower case. So these are the first 20 elements of the periodic table which are written in their symbols that are followed even today. All right. Now, Dalton in his theory spoke about atomic mass. He did say atomic mass. Now, how do we measure this mass? You must be thinking, ma'am, it is such a tiny particle, such a tiny entity. How do we measure it, ma'am? We cannot even see it. So how do we measure it? Very nice question. A really nice question. The answer to that question is given right over here. They came up with the term of relative atomic mass. Relative, that is based on a comparison. How did that happen? Let's see. See, the most remarkable concept of the Dalton's atomic theory proposed atomic mass. right? Now, obviously, I have a certain mass, you have a certain mass. So, these atoms that are there, they are the building blocks. It's their mass summing up together to give us the mass that we have and all the matter around us that it has. So, what exactly is the mass of an atom? Nice question. So, according to him, each element had a characteristic atomic mass. Each element had a characteristic atomic mass. This is one thing you need to be careful with. And then the theory could explain the law of constant proportions so well that scientists were prompted to measure the atomic mass of an atom. They were like, come on, yeah, let's find out. Let's find out the mass of this atom. They were prompted. They wanted to know that this theory, which is so precise in so many ways, how do we calculate the atomic mass? So, determining the mass of an individual atom was a relatively difficult task because they are tiny, right? It was very difficult. So, relative atomic masses were determined. Relative atomic masses were determined. Let me give you an idea of this. So, basically, they came up with the mass of one element, and based on that element, they decided the mass of all the other elements. All right. Based on that element, they decided the mass of all the other elements. How? By keeping it in comparison. Okay, using it as a reference point. All right, bacha. So, using the law of chemical combinations, the compounds were formed, right? So, how did this relative atomic mass come into picture? So, the term AMU, which basically means the term amu, all right, which according to latest IUPAC recommendation is now used as unified mass, but this amu is nothing but atomic mass unit. Okay, atomic mass unit. But now, based on the latest convention, it is written as unified mass. All right. So, let us take the example of the compound carbon monoxide formed by carbon and oxygen. All right, carbon and oxygen. It was observed experimentally that 3 grams of carbon combines with 4 grams of oxygen to form carbon monoxide. That is, 3 grams of carbon requires 4 grams of oxygen. So, 1 gram of carbon would require how many grams of oxygen? It would require 4 by 3 grams of oxygen. All right. Now, this as equal to, now what we can do is, suppose we define the atomic mass unit, okay, as equal to the mass of 1 carbon atom. Okay, mass of 1 carbon atom we are defining it as. Then we should assign carbon atomic mass 1 and atomic mass of oxygen as 1.33 U. 1.33 U, because for 1 gram of carbon, 4 by 3 grams of oxygen is used. That is 1.33 only, no? And this 1.33 is coming from where? In comparison to that of carbon, right? So, for 1 U, okay, the carbon, for 1 U of carbon, 1.33 U of oxygen is required. However, it is more convenient to have these numbers as whole numbers, all right, or as near to a whole number as possible. So, what do we do now? If we sit and start calculating with respect to compounds, then again we are getting different masses of different compounds, right? Here carbon, here oxygen is 1.33 grams, right? 1.33 U, right? But in water, it's not the case. There it is going to be different. All right. So, we need to, have a reference. So, where did that come from? So, initially scientists took 1/16 of the mass of naturally occurring oxygen as the unit. All right. But later it was discarded because, oxygen reacted with a large number of elements and formed a lot of compounds. All right. And this atomic mass unit gave mass of most of the elements as whole numbers. All right. So, now what to do? So, in 1961, the universally accepted atomic mass unit, okay, which one? Carbon 12 isotope. Carbon 12 isotope was chosen as the standard reference for measuring the atomic mass, okay, atomic mass. Now, once the atomic mass unit is given as is equal to 1/12 of the mass of one atom of carbon 12, C12. All right. And the relative atomic masses of all elements, the relative atomic masses, that is based upon the comparison, the relative atomic masses of all elements have been found with respect to an atomic or atom of carbon 12. Now you must be again thinking, ma'am, okay, carbon 12, got it. 1/12 is mass, its mass is also clear. But isotope? Isotope, ma'am, what is isotope? I'll help you understand what an isotope is. In simpler words, if I have to say, isotopes are those, they are belonging to the same members of the family. Okay, same members of the family of an element, which will have the same number of protons but different number of neutrons. They will have the same number of protons but different number of neutrons. So there we have C12, C13, C14. In C12, the number of protons is 6 and the number of neutrons is 6. Okay, in C13, the number of protons is 6 and the number of neutrons is 7. In C14, the number of protons is 6 and the number of neutrons is 8. I hope you know that in an atom, there is a nucleus. Inside the nucleus, there is a neutron plus proton. It is this neutron plus proton which determines the mass number. So in case of isotopes, the protons are constant. The number of protons remains same. It is the neutrons which vary in number. Alright, the most easiest way of me helping you understand relative atomic mass is, let's say you have gone to a shopkeeper, okay, you have gone to a shopkeeper and your mother asked you to get some fruits. So you've gone to a fruit vendor, alright, now you want to buy some fruits. But the shopkeeper, the vendor, he forgot to get his measuring weights. Now what did he do? He took a watermelon. He cut this watermelon into 12 equal parts. Alright. And now what he did was, he started weighing all the other fruits that he had, which was apples, bananas, grapes, with respect to these unit, this one single unit, okay, the divided portion of watermelon. Alright, so with respect to that one piece of watermelon, you got 2 apples, you got 4 oranges, you got, some grapes, you got 6 bananas. But although there was no weight as such, right, but you had an idea that, alright, with respect to this particular piece of watermelon, I have got the rest of the fruits. So that is how relative atomic mass, okay, comes into picture. Because obviously, it is not going to be easy, alright, for scientists to sit and measure the mass of every element, because these elements are made up of tiny atoms and these atoms are not even visible to our eyes. How will we measure them? Alright, so this is about their measurement. Alright, and based on this, the first 20 elements along with their atomic masses have been presented to you. Alright. Now, alright ma'am, atoms understood, atomic mass understood, they are very tiny, okay ma'am, they cannot be created nor destroyed ma'am, but how do they exist ma'am? Very simple. These atoms of most elements are not existing independently, okay, they form aggregates to form molecules and ions. So atoms combine, and they can combine of the same element or of different elements to give rise to molecules or ions. All right. So let's now see about a molecule. All right. A molecule is a general, okay, it is a group of 2 or more atoms, okay, that are chemically bonded. They are bonded together. That are chemically bonded together, that is tightly held together by attractive forces. By attractive forces, we already know that there are molecules and there are, attractive forces, interatomic attractions, intermolecular attractions, okay, intermolecular forces. We have learnt about it in detail, right? So they are bonded together and they have this force of attraction, which is nothing but molecular forces of attraction are present between them. Okay. Now, this molecule can be defined as the smallest particle of an element or a compound that is capable of independently existing. Atoms generally don't independently exist. They combine. All right. And they combine, and what do they give? They give us molecules or ions. All right. And shows all the properties of that substance. It shows all the properties of that substance. Now, the molecule of water will show all the properties of water, right? Because atoms combine to give rise to molecules. Molecules combine to give rise to that particular compound. Let's say for water H2O. Two atoms of hydrogen combine with one atom of oxygen to give us water. Whereas O2 is also a molecule where two atoms of oxygen only combine and give us oxygen molecule. Alright. Atoms of the same element or different elements can join together and form molecules. Alright. Now, molecule of an element. Now, this is important. See, the molecules of an element are constituted by the same type of atoms, Molecule of many elements such as argon, helium, etc. are made up of only one atom. They are made up of only one atom of that element. Mostly, it is these noble gases, all right, helium, neon, argon, all of them, all right, which exists as a single atom, even in their molecular form. All right, are made up of only one atom of that element. But this is not the case with most of the non-metals. For example, a molecule of oxygen consists two atoms of oxygen. Hence, it is known as diatomic. So, ma'am, if it is having one atom, then it is monoatomic. All right. And if three atoms of oxygen unite into a molecule, instead of usually two, we get ozone, O3. All right. So, the number of atoms, all right, constituting a molecule is known as its atomicity. And here are a set of examples: argon, helium, monoatomic; oxygen, hydrogen, nitrogen, chlorine, they are diatomic; phosphorus and sulfur. Phosphorus is tetraatomic, it exists as P4, and sulfur is polyatomic, it exists as S8. All right. Sodium, iron, aluminium, copper, these are all metals. Metals generally exist as monoatomic. Here, all right, molecules. All right. So, molecules of compounds, atoms of different elements join together in a definite proportions to form the molecules of compounds, and we are already aware of this when it comes to water, nitrogen. Try doing it for carbon dioxide. It is 1:8, 14:3 by their mass. Now, what are ions then? What exactly are ions? Ions are charged entities. So, compounds composed of metals and non-metals containing charged species are known as what? Ions. And ions may consist of a single charged atom or a group of atoms that have a net charge on them. A group of atoms can also have a net charge on them. So, the process by which ions are formed is known as ionization. And the charge can either be negatively charged or positively charged. And the group of atom carrying a charge is known as a polyatomic ion. Now, neutral atom. See, the neutral atom is there. All right, neutral atom is there. Now, we know that in a atom, we learn about this in detail and we do structure of the atom. But for now, I'm giving you a brief idea. In the atom, there is this nucleus where there is neutron and there is proton, and around this nucleus, we have the electron. All right. We have the electron. Electrons are negatively charged. In a neutral atom, beta, the number of protons is equal to the number of electrons. That is why it is neutral, because protons are positively charged and electrons are negatively charged. So, if the number of protons is equal to the number of electrons, it automatically becomes what? It becomes neutral. It becomes what? It becomes neutral. But then these electrons are capable of movement. They can be gained or they can be lost. Metals, what do? They lose their electrons. Non-metals, on the other hand, they gain electrons. Why do they do that? We will again learn about that in structure of the atom. But for now, I want you to understand that metals, they lose their electrons, and non-metals, they gain electrons. Now, metals, upon losing the electrons, now what happens is the number of protons is equal to the number of electrons. If the metal is losing the electrons, then the net charge on that particular atom is going to be what? Positive. That is why they are known as cations. Positively charged entities are known as cations, and they are formed upon losing of electrons. All right. Now, when I talk about anions, now non-metals are the ones which are gaining electrons, right? So, when these non-metals, they gain electrons, by gaining of electrons, what happens? In a neutral atom, the protons are equal to electrons. If it is gaining electrons, the net charge on the atom is what? It is going to be negative. Why? Because the number of electrons are going to increase. Thereby, an ion is formed, and these anions are nothing but negatively charged entities which are formed upon gain of electrons. So that is how ions are formed. All right. Now here is the list of all the ions. You have hydrogen, sodium, silver, potassium, lithium, ammonium, barium, calcium, copper, magnesium, zinc, lead, iron, aluminium. All of these are nothing but metals. All right. That is why they are forming cations. That is positively charged species. Now, when you look over here, these are anions. All right, and all of them are what? They are non-metals. That is why they are forming anions, which are nothing but negatively charged species. All right. And you can see over here hydroxide, nitride, not oxide, sulfate, carbonate, hydrogen carbonate. All of them are what? All of them are nothing but, they are nothing but polyatomic. All right. So these are the various ions. Now here again are some other list of polyatomic ions. All right, some other list of polyatomic ions. As you can see over here, ammonium, hydroxide, nitrate, sulfate, carbonate, phosphate, chromate. Then you have acetate. This is for acetate, peroxide, permanganate, hydrogen sulfate, hydrogen carbonate, hydrogen phosphate, dichromate, hypochlorite. All of these are nothing but polyatomic ions. Now, how do you write a chemical formula? Ma'am, yes, ma'am, these atoms are there. Atoms are forming molecules. We are getting compounds. But how are they combining? All right. So, how to write a chemical formula again is very, very important. The chemical formula of a compound is a symbolic representation of its composition. That is how many atoms of which element is combining with which element to give rise to a specific compound that you need. All right, it is a chemical representation of its composition, and this chemical formula of different compounds can be written very easily. Okay, for this we need to learn the symbols first and the combining capacity of these elements. Now, what is this combining capacity? Combining capacity is nothing but the valency, the charges that you saw. The charges that you saw, that is the combining capacity of that particular element. So, valency can be used to find out how the atoms of an element will combine with the atoms of another element to form a compound. So, the valency of the atom of an element can be thought of as the hands or atoms of that atom. How can we understand this? Let's say there is an octopus and there is a man. We know octopus has 8 arms, right? And you know that man has 2 arms. Now, how will this octopus get hold of the man if, and how many man can it get hold of with using all its arms? So, we as men, that is we as humans, we have 2 arms. So, if the octopus wants to get hold of my hands or of me, then it is going to use both its arms to hold both my arms. But it has 8 arms. That is, it will use. Octopus is going to use all the 8 arms to hold 4 people. Okay, so the combining capacity of octopus is 8 arms. Why? Because it is with these 8 arms it is getting hold of man. And that of man, And that of a man is 2 arms, right? So combining capacity of man becomes 2. All right, moving on. Moving on. So how do we write the chemical formula? How do we write the chemical formula? So the valencies or charges of the ions must balance. All right. Next is, when a compound consists of a metal and a non-metal, the name of the metal always is written first. For example, in calcium oxide, calcium is the metal, it is written first. Calcium oxide, sodium chloride, sodium is written first. Iron sulfate, iron is written first. All right. Where oxygen, chlorine, sulfur are all non-metals, okay, which are written on the right side, whereas the metals are written on the left side. All right. Another thing is, in compounds formed with polyatomic ions, the number of ions present in the compound is indicated by enclosing the formula of the ion in a bracket. What do we use? We use a bracket. And writing the number of ions outside the bracket. We write the number of ions outside the bracket. So how do we write the chemical formula? All right. Let's take the example of, what do we take? Let's take calcium oxide only. So first you are going to see the symbols. You're going to write the symbol first. Calcium, Ca. Oxide basically comes from oxygen, O. Then you're going to write its valency, or I would rather say charge. Let me use the term charge. It is going to be +2 for calcium and oxygen -2. Okay, now what are we going to do? We are going to crisscross. That is, calcium is going to get the charge of oxygen and oxygen is going to get the charge of calcium. So we are going to get Ca2O2. Also, when we are writing it down, you only take the magnitude. You do not write the charge in the formula. All right, Ca2O2. Now you want to have this in the simplest ratio. So simplest ratio, that is 2 gets cancelled, CaO. All right, let's take another example. Let's take sodium chloride. What is the symbol of sodium? Na. Chloride, Cl. What is the charge? +1, -1. Balance. Na1, Cl1. Now, but when 1, 1, you don't have to mention it as 1 over there. It is understood. NaCl. It is understood. All right. Now, so let's do a question. The formula of sodium oxide. All right. So again, the same thing. Sodium oxide, the symbol is Na. Oxide O, charge +1, -2, crisscross Na2O. All right. Then aluminium chloride. All right. Symbol Al, Cl, charge +3, -1, Al, Cl3. It's going to be sulfide over here. Sodium sulfide, sodium Na plus S, -2, crisscross Na2S. Magnesium hydroxide, MgOH. Magnesium has the charge +2, OH -1, crisscross MgOH2. So this is how you will write the formula. All right, beta. So this is for sodium oxide, sodium sulfide, aluminium chloride and magnesium hydroxide. All right. All right then, kids. So with this, I would now like to thank you all. Kids, for being a part of today's session. And I hope that this summary lecture has helped you understand this chapter better. So until we meet next, keep smiling, keep revising and stay healthy. Until then, bye-bye.